Looking at the top of the engine, you'll find the ignition coils that we currently have removed. You'll find that there's 4 ignition coils, 1 per cylinder, and then as well as 4 spark plugs. Taking a look at our wiring diagram, you'll find that there's only 2 wires that run to each coil pack, meaning that the driver circuit for the ignition coil is found in the PCM instead of being built into the ignition coil. And then we have constant power running to each coil pack from the main relay, so as long as the key is on, there's positive potential at the coil packs. And then to turn on the coil pack, the PCM will then ground the coil and then shut off that ground to then activate the coil. Another thing to keep in mind is that these coil packs can be tested since they are only 2 pins. You can test the primary side for resistance and you should see about 0.75 ohms of resistance plus or minus 15%. And then on the secondary side, you should expect to see around 5.9 thousand ohms of resistance plus or minus 15%. Testing the primary side of the coil, we were seeing about 1.2 ohms of resistance. Then when we were testing the secondary side of the coil, we were seeing about 5.8 thousand ohms of resistance, meaning that this coil was good. The next component we tested was the spark plug. You can see that by testing across the center electrode, we were getting about 4,000 ohms of resistance, meaning that there is a traditional resistor inside the spark plug. The next thing we tried testing was a divorced coil from a separate vehicle. Because this coil is divorced, you have to test across the 2 outputs for the secondary winding, and then the other 2 connections on the bottom side to test the primary side. They are separated and you cannot test them by probing the secondary and primary side at the same time. You can see that on the secondary side we were getting about 5.5 thousand ohms of resistance. Here we're testing between the primary side and the secondary side, and since this is a divorced coil, you can see that we have no continuity. Then we tested the primary side and you can see that we got 0.7 ohms of resistance across the primary coil. The next tool that we used was a spark gap tester to see what kind of voltage the coil was capable of generating. You can see that we were able to generate up to 40,000 volts using the spark gap tester, meaning that this coil had no issues generating a high voltage, very strong spark. The next thing that we did was probe into the driver's side of the ignition coil so that we could see how it was behaving with a picoscope. Here you can see the voltage pattern for the primary side of the ignition coil. You can see that starting out at source voltage, it then drops to near 0 when the PCM turns on the ignition coil. And then when the PCM cuts power to the ignition coil, that's when the magnetic field collapses and the voltage spikes. And then you can see it's sustained for a minute there as the spark arcs across the spark plug gap, and then it balances back out to source voltage. The other thing that's possible to observe is the amperage draw of the coil with the inductive pickup clamp, and you can see how it ramps up slowly and gets to about 9 amps of current draw before it's shut back off. Here you can see multiple times that the ignition coil was fired, and then in between there you can see little blips that look like noise, and this is actually when the ignition coils on the other cylinders are firing, causing a little bit of interference in our readings. Here it's possible to see how long the PCM turns on the ignition coil for, which is about 2.2 milliseconds. The other thing you can see is our current ramp, and you can see how there's really no time that our coil spins being fully saturated. This is because this car has a adaptive dwell time, meaning that the PCM will only turn on the coil just long enough to fully saturate, and as soon as it's fully saturated, it'll be shut back off. In this test, we hooked up to the crankshaft position sensor to see the relation of how the ignition is triggered in relation to the crankshaft. And you can see we're hooked up, the blue signal is cylinder number 1, and the green signal is cylinder number 3, because that is the next in the firing order. And you can see how those two are firing on the first 360 degrees of rotation of the crankshaft because this is a 4-cylinder engine, and then the other 2 cylinders will be firing on the next full rotation of the crankshaft. Since in this test we're only hooked up to 2 cylinders, you can see that when we zoom out the image, you can see how there's just a full rotation of the crankshaft where nothing happens, and this is because this is when the other 2 cylinders are firing. But you can see how it's a repeating pattern and how the coils are controlled relative to the crankshaft.
Taking a look at our wiring diagram here we have the diagram for all 6 ignition coils. And for our testing purposes, we are going to be focusing on coil number 4. Here with this black and yellow wire, that is our power wire coming down to this junction connector. This yellow wire right here is going back to the PCM. That is going to be our signal wire that the PCM sends a signal to the coil to have the ignition control module that is internal to the coil turn on to power the coil. And then here's our black wire that is going to be part of our common ground between coils 4, 5, and 6.
Looking at our communication signal, this being the signal from the PCM to the ignition module inside the coil pack, you can see that it's just a simple 5-volt square wave signal that tells the ignition module to turn on the ignition coil. And then you can also see the little bumps where other ignition coils are causing noise within the signal whenever they're activating. In this image, you can see we've added in the current ramp alongside the square wave signal, and you can see how the square wave signal is also just simply the dwell time of the coil, and how the current just acts as a normal current ramp like any other coil.